In this video, I'm going to interrelate sort of the ideas of potential energy, voltage, work, and the motion of an electron, okay? So we've already talked about electric potential energy, okay? And we gave the unit in terms of joules. So electric potential energy, we've been calculating in joules, okay? However, a joule is a very large unit, okay? We're using joules for like the movement of like a 5 kilogram object or a person, and then we try to use a joule and relate that to, you know, something that's as tiny as an electron or as a proton. So we actually have a unit that we use for energy and electricity that's called an electron volt. So another unit is the electron volt, okay? We're in EV, okay? And the conversion is that 1 electron volt is equivalent to 1.6 times 10 to the negative 19th joules, which, remember, that's also the charge of an electron. So you can remember that value, okay? So just keep in mind that sometimes electrical energy will be given in electron volts, okay? But what's important is when we actually are going to start relating the potential energy of the electric potential energy that an electron or proton or some charge has. In all the equations up to this point, we're assuming that the unit is in joules, okay? And in the equation that I'm going to use today, where we relate potential energy to kinetic energy, the unit should be in joules. So if you're ever given this, you need to make a conversion between one and the other in order to have it in the proper unit, okay? So in the last video, I talked about a parallel plate situation where there's a uniform electric field, you know, sort of going through this plate, okay? So what can happen is if I were to place, like, let's say an electron, like right here, okay? And I put that electron in there. Let's just think about, you know, what would happen to that electron. If I were to set it there, I'm sort of holding it there. It is going to tend to want to fly right to the left. So it's going to want to go this direction. So here it has some sort of potential energy, and then when I release it, it's going to then convert to kinetic energy. So that's our old equation of the change in potential energy, remember, is equivalent to the change in kinetic energy, the law of conservation of energy, okay? So let's see how we can calculate this. Let's just say that there's an equipotential line right here, okay? And I'm just going to say that that right there is 5 volts, okay? So somehow we've got to relate the potential energy and the voltage and the charge, okay? Well, I know from my equation, my definition of voltage, that the change in volts is actually the change in potential energy over the charge, okay? So just solve for potential energy, okay? And you get that Q times V, or the change in V, is equal to the change in kinetic energy. Well, what is the equation for kinetic energy? Remember, kinetic energy is 1/2 mv squared. So QV equals 1/2 mv squared. So this is kind of an important equation to remember, because this tells you, or allows you, to calculate the movement of a charge, okay, of some specific charge in some potential difference. So let's do it for this problem right here, okay? So we have charge. Well, this is an electron, so we know the charge is 1.6 times 10 to the negative 19th. And that negative and positive, really the only thing that that value means is whether the energy is going in or going out. And we don't really need to, you know, concern ourselves with that. So we'll just put the magnitude of the charge is 1.6 times 10 to the negative 19th. The potential difference would be, you know, between 20 and 5, so that would be a 15 volt potential difference. If it started from this plate, then it would be a 20 volt potential difference. It's equal to 1/2, and then the mass, okay? So it's important to note that on your tables of information, you are told the mass of a proton and electron, so you always know the mass of these particles. And that is right here. So electron mass, neutron mass, proton mass. So it's 9.11 times 10 to the negative 31. So 9.11 times 10 to the negative 31 equals v squared. Okay, so I can figure out, how fast is the electron going to strike that surface. Okay, so just take 1.6 e to the negative 19th times 15 divided by 0.5 divided by 9.11 to the negative 31, and then second square root, second answer. 1, 2, 3, 4, 5, 6. 2.3 times 10 to the 6 meters per second. Okay, so that kind of brings home the idea that relates voltage, which is sort of the push on an electron or a push on a charge, and relating that to the actual motion and the physical motion and the velocity of that charge.